Okay, this is Jonathan Doolin. I am now in the middle of section 3 of Planetary Core and Surface Temperatures by Douglas J. Cotton, a paper published in 2013 by SSRN Electronic Journal. Now, in this section, he talks about basically this is something that happens sometimes in arguments is that somebody will say, oh, that number is very small. And they will just kind of like say, in an absolute sense, oh, 10 to 20 watts per meter squared. Oh, that number is very small. Um, so, they might be comparing it to a number such as this number here. This number is 2,598 watts per square meter. And this actually represents the intensity of the sun on Venus surfaces. On Venus surface, 2,597 watts per meter squared is how much energy is the intensity of the light on the Venus surface, and apparently only well, that was the number that's on that hits the outer atmosphere, but only 10 to 20 watts per meter squared actually reaches the ground. So he's saying that since that's such a small number, the light from the sun can't possibly be the cause of the heating. Oh, it could never be it could not possibly be the excuse for the heating. The trouble is that he's saying that the runaway greenhouse effect could not be the possible effect, but without a greenhouse at all, the actual temperature of Venus' surface should be 327 Kelvin. If there were no greenhouse gases and you just had perfectly transparent gases and vacuum, then the surface temperature should be 327 Kelvin. But the temperature is not 327 Kelvin. The temperature is like 700 Kelvin at the surface of Venus. But it is at the don't get me wrong, at the atmospheric surface it is around 327 Kelvin, but at the bottom of the atmosphere it's like 700 Kelvin. So when he says it is obvious that direct solar radiation could never account for an extra 400 degrees Celsius or not more, the this claim it is obvious is kind of that's not a legitimate argument. Whenever you say it is obvious that something could not happen, if you got one group of people saying, okay, this is the cause of the effect, and another person says, oh, it is obvious that's wrong, there's not really an argument there. There's no there. Okay, but it says Alberto Miatello has written a comprehensive 3-page analysis of what is happening on Venus. In section 8 of his paper, Refutation of the Greenhouse Effect, Theory on a Thermodynamic and Hydrostatic Basis, he shows that the calculated gradient, also known as adiabatic lapse rate, is evidence in the atmosphere and can be used to determine the surface temperature of Venus. And then he says, we will return to this calculated adiabatic lapse rate or thermal gradient in section 6, but it will be sufficient at this stage to explain that it depends upon the force of gravity and specific heat of the air or gases in the atmosphere. At this point, I am tempted to skim up until we get to section 6, because all we're getting here is just misrepresentation of the greenhouse gas theory, and maybe if we got to section 6 we would hear an actual representation of his alternative hypothesis. This says, if we know the gradient, we can imagine a graphical plot of temperature against altitude having that gradient. I can tell you what that looks like. That looks something like this, with temperatures through the troposphere going down, then through the next layer, tropopause, wherever this is, the stratosphere, the stratopause, the mesopause, the thermosphere. So the temperature is going, so this line here, this graph, 150, 200, 250, 300, represents the temperature, and you can see it's higher at the ground than it is at the top of the troposphere, at the tropopause. So yes, we can imagine a graphical plot of temperature against altitude having that gradient. We can, and I just showed it to you. The level of the plot is determined as the whole line moves up or down in parallel positions until an equilibrium state evolves in which the total outward radiation is equal to the incident radiation from the sun. Okay, so what we got here, like imagine if we had two doctors. You went to a doctor, went to two different doctors with your symptoms, and you go to the first doctor, and the doctor says, "Oh, I see what's wrong with you. You have these symptoms, and I'm going to tell you what caused those symptoms, and I'm going to tell you how to cure the problem." And you go, "Okay, well, I want to go have a second opinion." Okay, so you go to the second doctor, and that doctor says, "Okay, I can describe those symptoms to you. I can describe those symptoms." That first doctor who had an explanation for those symptoms and a cure for those symptoms is an idiot. But I can describe those symptoms. And that's what's going on here. The level of the plot is determined as the whole line moves up or down in parallel positions until an equilibrium state evolves in which the total outward radiation is equal to the incident radiation from the sun. So basically he's talking about this line here, the line of the tropopause. He's saying that he can move that line, that tropopause line, up and down. He's going to move that tropopause line up and down until the outbound radiation from that surface is equal to the inbound radiation coming in from the sun. So whereas greenhouse gas theory explains why this gradient is there, he's just saying, okay, there is a gradient, and I can move that tropopause anywhere I want so that I can get the input radiation equal to the output radiation. So, okay, he then says, the important point to note is that the parameters discussed in the above paragraph predetermine the thermal plot, and so we can calculate at what temperature the line would meet the surface. Okay, so let me talk about what are the givens here. Okay, the givens would be the temperature of the surface. If we measured the temperature of the surface, that parameter predetermines the temperature at the bottom of the plot. We also have, from the calculation I did back here, the temperature of Venus based on Stefan Boltzmann's law. We can calculate what the temperature should be at the top of the plot. And so Venus's temperature is about 700 Kelvin at the bottom of the plot, 327 Kelvin at the top of the plot. And so we can just, and we got the distance, how tall their atmosphere is. So based on how high the atmosphere is, what the temperature is at the base of the column, what the temperature is based on Stefan Boltzmann's law, everything, all of those values predetermine the thermal plot. So we can calculate at what temperature the line would meet the surface. Okay, maybe, okay, I may have, okay, what else? Let me figure out. Okay, I said we know I say we know the temperature at the bottom. He's saying we know the gradient. He's saying we know the gradient, and he's describing the gradient as being linear. So that's a little bit different from what I said. He's saying that we can predict the temperature at the bottom if we know the gradient. So that is a bit different from what I said. But but this is an important question. How do you know the gradient? If we know the gradient, and that's basically the question, is the gradient established? Isn't the gradient established by the thermal conductivity of the greenhouse gas? I think the gradient is determined by the thermal conductivity of the greenhouse gas. What is he going to say is the primary determinant of the gradient of altitude versus temperature? Okay, he says, notice that we have not used any information about back radiation or energy flows into the surface. It's okay. Yet with reasonable accuracy, we can calculate backwards what the surface temperature ought to be in order to leave us with both radiative balance and a correct thermal gradient. We can calculate backwards? Is that what he's saying? We can calculate... Okay, it seems to me that you're going to either have to calculate forwards or backwards. And if you're going to either have to start with the gradient and come up with the temperature at the ground level, or you're going to have to start with the temperature at ground level and calculate the gradient. But he's saying we can calculate backwards what this temperature ought to be in order to leave us with both the radiative balance and the correct thermal gradient. So it sounds like he's... How is he doing both? Calculate backwards. Okay, so this is, I guess we got to find out what his theory is. He's leaving it till section 6, I guess. I'm going to read this last paragraph here, and then I can't wait to go to section 6, because section 6 is going to talk about this thermal gradient. Where does he get this thermal gradient? Because I know where I get the thermal gradient. It comes from the thermal properties of carbon dioxide, the atmospheric, or the greenhouse gas. So he says, this accuracy of the surface temperature calculations, which can be made for Earth, Venus, and other planets, cannot be coincidental. One has to ask why we on Earth should be so worried about one carbon dioxide molecule in about 2,500 air molecules, when the atmosphere of Venus is nearly all carbon dioxide, yet the surface temperature is still able to be calculated in the same way. So let's go on to section 6, because he's not giving us any information on how he's actually calculating this thermal gradient here, but he says he does in section 6. Quantification of the thermal gradient. The derivative of the dry adiabatic lapse rate in Wikipedia, for example, is rather cumbersome. Starting with the ideal gas law, considering the effect of gravity on pressure, but then eliminating pressure in the final step anyway. I'll have to look at that. A much more logical derivation, which helps us understand what the actual process is, can be derived simply by applying the conservation of energy principles to every movement of a molecule in its free path along between collisions. It is only during collisions that the actual process of diffusion of kinetic energy takes place. So in the free path motion of a molecule, we can assume a purely adiabatic process in which the sum of gravitational potential energy and kinetic energy remain constant. Okay, can we? Sound, I think sound is an adiabatic process. If you look at the sound, you'll find that the equation for sound works out if you use the adiabatic bulk modulus of air. So in the free path motion of a molecule, we can assume a purely adiabatic process occurs in which the sum, okay, this, he doesn't have enough starting assumptions here to claim that he doesn't make enough restrictions on this, because there's things called adiabatic, there's things called isobaric. There's an isobaric process, there's an isovolumetric process, and there's a isothermal process. So there are many different types of processes, and there are also processes which don't fit into any of those categories, because maybe the pressure and the volume are both changing, so it's neither isovolumetric or isobaric. So in terms of an adiabatic process, actually the adiabatic process means that the amount of energy inside a gas is definitely not changing. So I would say almost by definition here, almost by definition of what adiabatic means, if he's talking about the free path motion of a molecule, okay, I'd assume is he talking about a collision? Okay, he's not talking about a collision. All right. I'm going to just think about a concept of the PV equals nRT. I'm going to actually write this a little bit different. PV, or add a, I'm going to add one more thing to this, which goes 2 over df u. And this additional quantity over here, U is called the internal energy of the gas. dF stands for degrees of freedom. For a diatomic gas, that degrees of freedom is 5. For 5 equals N2 or O2. CO2 has degrees of freedom of, I think, around 6. And it has to do with the ratio of their specific heat, joules per mole Kelvin, in divided by the ideal gas constant. So let's take, okay, I made a little table here because I want to state the specific heat at constant volume of N2 and carbon dioxide. These are going to be the molar specific heat. It's 5 halves times the ideal gas constant for a diatomic particle. Specific heat at constant pressure is a little bit more. It takes more energy to heat a gas at constant pressure than it does at constant volume. So the value here is 7 halves R. So here we've got specific heat at constant volume of 7 halves R and 9 halves R for the specific heat at constant pressure. I don't think that this, well, he's gonna find some relevance in these things, but this is a basic overarching equation that we're going to that I would stake my reputation on. Well, except that sometimes I goof and I haven't thought about this in months, so what if I've made an error? So it will, with the asterisk that I hope I haven't made a typo here, but basically this is it. The pressure times volume of gas is equal to the number of moles times the ideal gas constant times the temperature, which is equal to 2 divided by the degrees of freedom, which times the internal energy of the gas. And this is the kinetic energy of the gas, the total kinetic energy, which is rotational degrees of freedom plus vibrational degrees. So it's 2 over degrees of freedom times rotational kinetic energy plus linear kinetic energy plus vibrational kinetic energy. So like what happens with N2 and O2, they've got 3 degrees of freedom, 3 degrees of freedom in the form of linear kinetic energy, 2 degrees of freedom in the form of rotational kinetic energy, and then they've got 0 degrees of freedom in vibrational, whereas carbon dioxide has 2, 3, and 2, basically, degrees of freedom. So reading through his description here, it's not entirely an invalid idea. I'm just going to try to work through the problem myself, because the way I think the thought experiment that he wants to do here is to basically take a volume of air here at the tropopause that is about 10 kilometers from the surface of Earth, and then that is, I guess, we'll set it at 288 Kelvin. No, let's put it at 255 Kelvin. And we're going to drop it by that 10 kilometers in a gravitational field to the surface and see what is the temperature. The temperature when all of that gravitational potential energy has been put into the gas. First of all, let me point out a little problem with this idea. That this is something we definitely don't see in like the ocean. We don't see a system where the water far below the surface of the water is hotter than the water that is above. It's not as though somehow the water has gained kinetic energy by falling that distance. But I shouldn't poo-poo it too much. But like, I want to poo-poo it, because so I'm biased. I'm not gonna pretend I'm not biased, because I'm interested in acknowledging this idea, but I'm also interested in disputing it, because there is some reason I think that we have to dispute it. Well, here's an idea. Here's an idea. I've got a stack of board games on the shelf in my room. I've got some board games that are up here on the top of the shelf. I've got some board games down here at the bottom of my shelf. Do I have any expectation that this board game is going to have a higher temperature than this board game because it is lower down? I mean, if I had dropped them both, if I had dropped this board game to that surface and dropped this board game to that surface, then yeah, this board game would be messier. It would probably have its pieces all strewn about the room and everything like that. But that phenomenon isn't really going on. That's not something that's occurring. But for the sake of argument, let's say that did occur with this gas. We've got this gas, and it falls from the troposphere at 10 kilometers up to into a container that is 10 kilometers below it, and it's going to gain on its way. It's going to gain some kinetic energy, and we're going to calculate how that kinetic energy translates into temperature. Okay, so the density of air is 1.29 grams per liter. That is, I think, 1/1000th of a meter cubed. So I'm going to go ahead and make it 1.29 kilograms for a cubic meter of air. Okay, so if we do that, we get a value of 126.420 joules that the air will gain if it drops 10,000 meters in a gravitational field of 9.8 meters per second squared, or newtons per kilogram. Okay, so the specific heat of air at constant pressure is 1005 joules per kilogram per Kelvin. So the amount of energy is going to be equal to mass times specific heat times delta T. So we're going to put delta T equals E over mc. And the result is actually 97.5 Kelvin, if I've done this correctly. So that's a pretty impressive number. It's quite a bit larger. It's actually quite a bit larger than the value that we actually have. And let's talk about an environment where that would be the actual cause of the temperature change. If we had a situation where the Earth was right here and we had gases swirling around the surface of the Earth at 10 kilometers above our heads, and that gas occasionally dropped down 10 kilometers to the surface, then yes, there would be the difference in the temperature of the gas out here that is falling through a vacuum without any opportunities to slow down. If you actually had those gases from the top surface of the atmosphere falling directly down to or at any angle towards the surface of the Earth, then yes, it would probably be that the difference in temperature of the gas up here and the temperature of the gas down here would be about almost 100 Kelvin. Even more so if the swirling gases were coming from way up there. Goodness, you would quite noticeably heat the Earth if you have a whole lot of gas falling all the way from the troposphere to the surface of the Earth. This would considerably heat the Earth. So this is a thought experiment. Let's go through it again. Let us consider a thought experiment in which such a region of air of mass m all happens to move downward by a small height difference. I didn't use a small height difference. I used a large height difference. I had it go all the way from the tropopause all the way to the surface of the Earth. So I used a large height difference, h, 10,000 meters. In an atmosphere where g is the acceleration due to gravity, I did that. I said 9.8 meters per second squared. The loss in potential energy will be the product mgh, and I did that, and that came out to be 126.4 joules for a cubic meter of air. And he said, because a force mg moves the gas at a distance h. That's right. But there will be a corresponding gain in kinetic energy, and yes, that was essentially my assumption, and that will be equal to the energy required to warm the gas by a small temperature difference T. And I calculated that the temperature difference here which is the energy change divided by the mass of the air divided by the specific heat of the air. It's going to be 97.5 Kelvin. Okay, so then he says this energy can be calculated using specific heat. This calculation yields the product mc sub p t. He's written mc sub p t equals mgh, calculated, so that would calculate t equals mgh over mc sub p. Only thing different is that I called that E over mc sub p. So yeah, that is essentially the exact thought process that I went through. And I came to the conclusion that the change in temperature would be 97.5 Kelvin for air dropping from the tropopause. Okay, but T over H is the thermal gradient. Now, okay, so T over H, the thermal gradient that I got was 99.5 Kelvin over 10,000 meters. So the gradient predicted by this theory is the temperature change of 97.5 divided by the height of the atmosphere is just 10,000. The gradient experimental, the experimental gradient in this case for Earth and the tropopause is about 33 Kelvin in 10,000 meters. So this phenomenon actually predicts a much, much greater gradient in temperature than what we have experimentally. But I don't think that's the greatest flaw with it. The bigger flaw with this model is that it's not happening. We simply do not have air falling from the troposphere down to the ground. There may be occasions where air does fall in from the ground, from above. Actually, that probably comes in commonplace. Whenever you have a low density air mass below a high density air mass, you're going to have the high density air mass displacing the low density air mass. So, but if we imagine that scenario with a high density of air mass over a low density of air mass, what happens then is that we end up with something like maybe this, with the high density in the middle and the low density on the outside. Actually, it's not even low density very much anymore. It's more like a cold front. It's probably a cold front. Or actually, maybe it's a warm front. I don't know. I'm not a weatherman. Okay, so the high density air comes down. But does the high density air actually have higher kinetic energy when it gets down here? Probably not. This does. What happens is it transfers the kinetic energy to there, and it does work. So work comes out of this dropping gas and does affect the low density gas around it, and it pushes it outward. So it does work on the low density gas. And so some of that anyway, that energy, it's kind of chaotic. Some of that energy goes to pushing that, so that goes into so when it causes large masses of gas to be pushed out, that's called convection. But it also might, some of the energy would be heating. Some of the gravitational energy would be converted to heat, and some of the gravitational energy would just be conducted into the gases nearby. and probably some of it would just be radiated out. So you got a lot of different places where that gravitational potential energy could go, but in general there is sort of a flaw in this idea of the dry adiabatic lapse rate. Let me jump to the Wikipedia. Okay, it appears that I am going to have to review exactly how the PV curve works in an adiabatic process before I can really go into this, because I've worked through the derivation. It's like a 10-step derivation involving some algebra and some calculus to figure out what the PV curve for an adiabatic process is. But right now, I don't have it really memorized, but I've just written it down somewhere. Okay, I'll put it on the screen in front of you. Let's see. Can I make that bigger? There we go. So we start with a 2 over degrees of freedom times the internal energy of the gas is equal to pressure times volume. Then we do a total derivative of this, which over here, 2 over degrees of freedom du actually is, I think, is that 0? I was thinking that in an adiabatic derivation, the du was 0, but I do not have du as 0. I have minus pdv. So let me look at step C down here. It says in step C we are applying the adiabatic condition. Because there is no heat exchange, the only contribution to the change in internal energy is the work done on the gas. Okay, so there is no heat exchange, but there is work. There is an exchange of work. So it's not du equals 0, it's du equals negative pdv. Du is negative pdv because work done on the gas is shrinking it. Like I said, I I didn't remember the derivation. I just remembered doing it. But yeah, so work is done on the gas here. And then that negative pdv and this pdv kind of combine over here on the left-hand side. So we got dv over v times degrees of freedom plus 2 over degrees of freedom equals negative dp over p. Then we integrate both sides. This turns out to be natural logs, and we have pi vi to the gamma. Gamma is this value here, degrees of freedom plus 2 over degrees of freedom, equals p final times v final to the gamma. So what I've got written here is basically gamma times dv over v equals negative dp over p. And they have written it just a little bit differently. P dv equals negative v dp over gamma. And let's see what else they have here. First law of thermodynamics is that delta U, the change in internal energy of a gas, is mc dt. That they've got mc sub v delta t. Actually, I do not write c sub v here, but I guess that is c sub v, because that would be the heat, specific heat at constant volume, which means no work is done there. Minus p dv minus p delta v. I guess this is minus p delta v. So p dv here is minus v dp over gamma. So except for its sign difference, because I use work on the gas, they appear to be using work done by the gas, maybe. But they've replaced this minus pdv minus p. They put a plus pdv for some reason. Plus pdv is the same as minus vdp over gamma, and then he's got minus VdP over gamma there. And then he's got 0. But I do not think... No, I do not have 0. No. There's something going on weird with the sign change and other things like that. So I don't know if I agree with this here. But while I can't follow the reasoning right now, I do see that the number that they've got here, 9.8 degrees Celsius per kilometer, is pretty much the same as what I got here, 0.00975 Kelvin per meter, which would be 9.8 degrees Celsius per kilometer. I'll see if I can pick this up in the next video, because this video is getting really long.